All right, so then a lot of times I'd like to actually talk about the temperatures. So nitrogen is 3 to 1 below. Oxygen not as cold to be a liquid, but still about 300 degrees below zero. And then most people are familiar with dry ice and know it as a very, very cold substance, which it is. And it is something that you can be burned by. And so you have to wear gloves to handle dry ice. But it's interesting to point out that dry ice is carbon dioxide in its solid form, and that is only 70 degrees below zero. So carbon dioxide is naturally a gas around us, but it can be made into a solid, and that's the 70 below, so not as cold as nitrogen. The thing is, though, that it's actually, and this will be the next, when I'm talking about condensation and evaporation, as a solid, it is very, very condensed, and so it's also really easy to be burned by dry ice because it's a solid. It's not going to roll up your hands. What brings in the Leidenfrost effect slide. So the Leidenfrost effect is when something is so much hotter or colder, and there's such a difference in temperature between one object and another. So when we are working with liquid nitrogen, and this is actually something that's really good to explain to your employees, to have your employees understand, because one of the main questions I'm sure you get, and one main question that we get is, doesn't that burn you? Do you get burned a lot by the liquid nitrogen? And so we can talk about how the Leidenfrost effect actually makes it that, because our bodies are 98 degrees. And sometimes I'll actually I give that to the class. I'll say, how hot are our bodies? And most of them know we're about 98 degrees. And where liquid nitrogen is about 400 degrees colder than that, 300 degrees below, then we're able to actually put our hand in and out again, and it doesn't burn. It actually really isn't even touching our skin because it's boiling around it because of the Leidenfrost effect. Because this is so much hotter, our body is so much hotter than the cold liquid nitrogen. And so it's really, there's a water vapor protecting, a heat water vapor protection around our hand as we're putting it in and out, which you don't get with dry ice because it's not a liquid, it's a solid. Another thing I love to do, if you have the chance, and it depends on where you're at, is to show the Leidenfrost effect, kind of like water on a hot pan. If you have a frying pan that's really hot, and you put water on it, it will roll across the frying pan because of the difference in temperature. That's the Leidenfrost effect. So here, if you look at it, and here it's not working as much because it's soaking into the tabletop.
Let me go get a.
Well, okay. So,
Here's one.
Okay.
Nice that they clean them.
That's a good idea.
Instead of having.
Okay. Was it on top of you?
On top of the oven, but they.
Yeah. All right. So sometimes if I'm at a place with a stage, that I can pour it on the floor, but if the kids are sitting on the floor, I don't like to pour it on the floor because it's going to roll over to them, and especially where they're sitting on the floor, it could soak into their clothes. So I won't do it if they're sitting, but sometimes if they're in chairs on the floor, I'll pour it on the floor. But here we can show it with this. You can see how it just rolls across the pan as it sizzles across there. That's the Leidenfrost effect.
So it's levitating just by, like this diagram just talks about.
And it's kind of the same thing of being able to pour it across your hand. It just kind of rolls across it. It doesn't stay on my hand.
So it levitates away from your skin.
So that's the Leidenfrost effect. All right, I think it's time to do some evaporation. We're going to jump back to that. When things condense, they decrease 600 times in size, or in mass. when they evaporate, they increase 600 times in size. So the liquid nitrogen, all the liquid nitrogen that's here, actually is evaporating little by little because it's outside of the tank. It's been exposed to the air and to the warmth. And because of that, it's now taking up 600 times more space in our atmosphere. Well, what I'm going to do, these are Arrowhead water bottles, but I think also Nestle, and I actually have found that Smart Water has started to make them too, because the best part about it is this cap, that is the pop-off cap.
You can break it off.
So I've already broken that off. You want to make sure and have it broken off for some of these demonstrations. But that's the best water bottle to use because of that pop-off cap. So this one we're going to show evaporation. I'm going to drop this down here. So I'm going to get some more liquid nitrogen. I'm going to use just a small styrofoam cup to be able to pour it into the bottle. So, and this one actually kind of helps to be able to show as well, because they can't really see the liquid nitrogen when it's in the cup, but you can see the liquid nitrogen in the empty water bottle a lot easier. So it's evaporating right now. The liquid nitrogen here is now getting warmer because of the air around it, and it's evaporating. And as it evaporates, you can see a little bit of the fog. All of that fog is really the water in the air getting cold. So it's the water condensing into a fog or into a vapor. Now I'm going to put it in here. And you can see the fog, the vapor even more. And you can see that's the liquid nitrogen that's evaporating. As it comes out evaporating, it's also making the air cold. So that it looks kind of like a geyser or like a geyser. So that one's kind of fun to be able to show the evaporation. Now, along with that, there's another way we can do it. Oh, and actually, this is something that we'll talk about. This is an empty water bottle, and yet it's not floating. It's the empty water bottles are supposed to float, but it's not. And so we'll ask them, why is that? What's happening? Well, it's stuck to the bottom. It's frozen. The water froze the bottle to the bottom. Actually, if you take it off, you can see the impression of the ice. Okay, another thing to show the evaporation, because that was the direction I was going. Okay, so I'm going to do the same thing where I'm putting liquid nitrogen in the bottom here. I want to make sure I have enough there. So you have about, I don't know, is that about a half inch of liquid nitrogen in the bottom? All right, that doesn't have to be exact, but you want enough for it to fill the balloon. So I tell them, we have a measuring device, and if I keep it in liquid nitrogen, it's going to keep it cold, so it's not evaporating as fast. We've got a measuring device that's a balloon. As
it gets cold, then it has fewer bubbles inside the nitrogen inside the bottle, and it becomes more clear.
I can actually. Do you want to do this one? You do this one. No, I'll switch.
Nope. Stop.
All right. There are times when Jerry and I will tag team, and there are specific things that he does really well. I'll have him do that one, and then I'll do another one. So.
But if you put the balloon on inside the bowl with the nitrogen, then it doesn't blow up while you're trying to put it on. If you've got it on the table, it's evaporating where it makes it hard to get the balloon on.
Yeah, and I haven't done that. But that's something you can also talk to the class about, to the people that's doing it. You have it on here. You want to make it so that no air can get out. So the only air that's getting into the balloon is the liquid nitrogen evaporating. So it's just nitrogen gas. But when I have it here in the bowl with the liquid nitrogen, it's not evaporating very fast. You can point that out. You say, look, the balloon's really kind of staying the same. It's not getting bigger. So that means that the liquid nitrogen is not evaporating, because if it were evaporating, it would be evaporating 600 times.
The nitrogen inside the bottle.
Yeah.
Is not.
Yeah. Not as much anyways. It's a little bit. If I take it out of there it's starting to grow a little bit because the air around it is cold. It is warm. It's actually getting the liquid nitrogen warmer now, and it's starting to evaporate. I'm afraid I have a...
Is there a hole?
I might have a hole. All right. We're going to do this again because I think my balloon has a...
Oh, poor balloon.
All right.
Feels so bad for the balloon.
Do I still have enough in there, you think?
Yeah.
Okay. All right. So again, it's starting to evaporate a little bit, starting to get bigger a little bit, but not much. If I put it out in the air, it's starting to grow a little bit more, starting to evaporate. But if I put it in water, because it's condensed into a liquid, is 600 times more energy than the air that's a gas. So if I put it in here, it's going to evaporate and warm up even faster.
By 600 times. Oh, well, that's fun.
Yeah.
Oh my gosh.
Now, if you're doing a presentation with a lot of little kids, a lot of times I will actually pop the balloon off before it pops because
But
the loud noises.
But the kids that really have a problem with loud noises already have headphones.
Maybe they don't. You have to tell them to put headphones on.
I know, but they usually have them ready.
Yeah, you want to warn the teachers about it because we have had kids that will
autistic kids
that will try. Or sometimes it's just kindergartners and first graders.
Okay. All right.
So, however, you get up into the other grades, like second and third, and then even eighth graders, and they just love that. They love to see it pop. They love that it pops.
Now look at the shred. This is what's interesting. Because the cold air or nitrogen that's blowing it up, it makes the latex more stable. And it shreds when it blows up.
So it's able to stretch even farther than it normally would. And because of that, it has pressure on all points of the balloon. There's not just one pressure point that causes it to pop. It popped because it was pressured in every single point as the air was expanding. So
it makes it much louder than a normal balloon popping, though. Much louder.
All right, so now we're going to do the same thing.
I didn't plug my ear that time, and my ears ringing.
It actually wasn't ringing. I should have plugged mine. When I do this one, I don't usually tell them. Now, if I'm pouring this in, they notice that it's bubble solution. But I won't always tell them what it is. But I'm again pointing out that liquid nitrogen, since it's here in the bowl on the table, it's evaporating. And as it's evaporating back to a gas. It's evaporating 600 times. So I'm going to take this cup, roll it around in the bubble solution, and then flip it over and put it into the liquid nitrogen. And as the liquid nitrogen is evaporating, it's not going very fast, is it?
Well, it's because it's the bigger side.
It always works better on the other side. So
the smaller side of the cup acts more dynamic.
So I think what I'm going to do is to do the smaller. I also don't have as much liquid nitrogen in there. Yeah, I think I need more liquid nitrogen. I don't like how high this is, but I kept it on the thing. This is actually one that I'll sometimes do with birthday parties or with little kids, ones that they're smaller groups where they actually sometimes can be up around the table. We had an employee who actually asked to be able to do this with customers when it was a slow time. The customers were in the shop, but they didn't have anyone else he wasn't serving people at the time, and it was kind of a fun demonstration there. My bubble solution is not strong enough. So everything that's making that bubble come up is just nitrogen gas, pure nitrogen gas, because I've trapped it, and the liquid nitrogen, as it's evaporating, is coming up and filling the bubble, making a bubble. So it's the very same concept.
And I think because it's cold, it's staying more stable, and that's why it's getting so big. Because a typical bubble will not get that big. Now, one of the reasons it will pop is because it gets warm.
Yeah.
Okay. Because a cold bubble is more stable than a.
All right, and I can always just lift it up and it goes back down. Then we actually found that when you do the other side and then flip it over, because this side is warm, it's going to make the that didn't. I think my bubble solution is more cheap. It seems too thin.
I think you're.
So I'll say this is the same concept as the balloon popping, except it's a bubble instead of a balloon. We're still capturing the liquid nitrogen gas as it evaporates and blows the bubble up.
Wrong balloon or bubble.
So I actually do think my bubble solution is a different brand. I don't know. It just doesn't seem to be. Maybe not.
I mean, it's working well. It's just.
And again, bubble solution you can find really cheaply. I find them at the dollar store. I do use it again. It's actually really cool when you get the vapor inside of it, because the I will at the end of the presentation I'll pour this back in the bottle. It still uses up some of it. I eventually have to replace it, but not as much. Like this isn't a waste. I usually, and there are some times actually when I've actually just done the bubble as hand soap and water. It doesn't even have to be a bubble solution. Just hand soap and water.
Dish soap.
Yeah, and that's actually what my the employee this we actually got from one of our employees. He figured this out, and I thought that is so cool. It's such a good idea. So it's not something that it's something that we added to show the condensate and to show the evaporation. Yeah. All right. Next one is the ideal gas law. So we're gonna take this. Do you want to do this one?
No, go ahead.
Okay. All right. Here, I'll move this down on the table. Ideal gas law. Sometimes, especially if they're old enough, like in junior high, I'll ask them, what do you think that P, V, and T equals when it comes to P, V equals T? Usually equations we only see numbers, but in this case, they're letters, and they're letters that stand for something. So, and they'll come up with like time and I don't know, some of the different things that they'll decide. But we come down to pressure times volume equals temperature. Now, what I'll often say is, an equation, even elementary kids know equations. Even the first graders know 2 + 2 = 4, but that